MAT6374 Topic 3 Solid Oxide Fuel Cells. What manufacturing processes are being used to fabricate these devices? So this slide shows micrographs of current planar architecture solid oxide fuel cells. These are devices that are based on powders that are processed either to be dense, as we can see on the right hand side here, the electrolyte is a very dense ceramic, whereas the electrodes are required to be very porous. So research and development is focused mainly on the materials development and the cell design. However, there is a push now towards commercialisation of cells and component manufacturing and improving the performance, and both measures are really aimed at reducing the costs. So processing these devices currently is very costly, and we need to get the cost down. Most companies are now focused on the planar anode supported solid oxide fuel cell design with a thin electrolyte layer. So you can see in the left hand diagram here is a solid oxide fuel cell where the electrolyte, the 8YSZ, is as thin as 16 microns. And you can see here that between the cathode and the anode we also have other functional layers which interface to try and help with the performance of the device. So in the case of R&D now, sometimes we've got more than the three layers associated with the cathode, the electrolyte and the anode. We have these interfacial functional layers at the cathode and the anode to help with cell performance. So just to recap, we did talk about planar and tubular designs previously, and both have their merits. What we also talked about was whether the planar design was electrolyte supported or electrode supported. And you can see here that for the planar design, if the electrolyte is thick, then this means that things are generally gas tight. The problem with the anode supported or the electrode supported solid oxide fuel cells is that the electrolyte layer can be very thin, as we seen previously, somewhere between 10 and 15 microns, and if that's not completely dense and we've got porosity, then the cell might not be gas tight. So this is an issue with electrode supported solid oxide fuel cells, that gas tightness may be an issue due to unacceptable residual porosity associated with a thin electrolyte layer. And as we said previously, the big issue here for the planar versus the tubular solid oxide fuel cells is one of power. It's what we get from the planar designs. The durability comes mainly from the tubular design, whereby it is easier to seal and they are less prone to leaks. So let's finish up this process here of the design. So what we can see on the left hand side of this diagram is the electrolyte supported cell. So this is a self-supporting configuration. One of the cell components has to be a thick layer which acts as the cell's structural support. So we have the electrolyte supported design on the left hand side and the electrode design of the electrode supported cell on the right hand side. So the electrolyte supported configuration possesses a relatively strong structure and is less susceptible to failure due to anode oxidation and cathode reduction. The downside is we have a high resistance due to the thicker electrolyte layer, so we need higher operating temperatures to minimise the ohmic potential losses in the electrolyte. So if we want to reduce the temperature of operation, then we can do this by using an anode supported or a cathode supported configuration with a thin electrolyte. Here the cell resistance or the ohmic resistances will be lower, but the production of a fully dense, gas impermeable, thin electrolyte layer becomes more difficult as we decrease the thickness of that electrolyte layer. This slide just summarises what we've said previously about performance related to gas tightness and current density. So let's now consider ceramic processing and how we make these solid oxide fuel cells. So we see two diagrams on this slide. On the left hand side is the apparatus that we use for tape casting, and here we're generally making layers somewhere of a sintered thickness between 10 and 100 microns. although some companies are now managing to tape cast down to sub-micron levels. This is typically what we call thick film processing. And the tape casting apparatus is rather simple and cost effective, and it's an excellent method to produce large area, thin, flat ceramic parts. The variables that are included in tape casting is a slip. This is the solution that contains our inorganic powders, what we want to deposit onto a polymer substrate, in this case mylar, and the thickness of the initial slip is dependent on the height of this doctor blade. So we have several processing variables, including the slip, the composition of the slip and its viscosity, the doctor blade gap, how thick we want to make that green ceramic layer, the speed of the carrier, that is how quickly the mylar polymer substrate is going from left to right, and then the drying temperature. On the right hand side here we see screen printing. Screen printing is a very simple technique to print on selected areas on ceramics. So we have our ceramic underneath here, and what we've got is we've got some kind of mesh, and then we simply smear some ink and rub a squeegee over the top of that ink so that we can deposit selected areas on our substrate of, say for example, electrode materials on top of our electrolyte. So both are very simple methods. The good thing about tape casting is that it can be a continuous reel-to-reel process, and therefore is very scalable on an industrial process. Screen printing, although it's very cheap and very simple, it's non-continuous, and this makes it rather more expensive. So by far the most important aspect involved in tape casting is the quality of your slurry or the slip. So for that we need very well controlled powders of composition and particle size and distribution. So powder characterization of your raw powder, say of your 8YZ, is very important. We then have to add solvents and dispersants, and then we mix that with the powder in a dispersion mill, and then we further add things like binders, plasticizers and solvent, and then mill everything up again in a secondary mill. So what you typically find is that your slip or slurry only contains maybe 50 or 60% of your inorganic solids. The rest of it is all organics that we add, or aqueous materials that we add to try and help with the rheology of the slip. We then de-air that mixture to try and get rid of bubbles to reduce porosity, and then finally we cast or print our tape. So let's go through each of those processes now in a bit more detail. So powder characterization is very important. So you need to know the chemical and phase composition of your material. So normally what happens is that most people that are involved with solid oxide fuel cells will commercially buy in their powders, but that still means that you need to do some bulk chemical analysis to look at the phase purity. So for example, we use X-ray diffraction to make sure that the phase that we are working with, in organic phase, say the 8YZ, is actually that fluorite based material. Often we are interested in the surface area, the surface analysis, and also any phase transitions that occur in these materials. So all the techniques that you covered in MAT6374 or 6665 rather, in materials characterization, are commonly used to analyse your starting powders. So X-ray analysis, spectroscopic analysis, and also thermal analysis. And what's also very important, not only the impurity levels, which may be deleterious to your electrical properties, you also are very concerned with the particle size and shape. So we need to do some microscopy to look at the particle sizes. We also need to look at the particle size distribution, and if those particles contain any pores, what's their porosity and what's their pore structure. So you really do want to start with very well characterized powders in terms of their morphology and their phase composition. The additives, well, there are many additives that we can put into our slurry solvents, which may be aqueous or non-aqueous. So aqueous in terms of water-based, non-aqueous in terms of things like alcohols and things like toluene. We often add surfactants. Cationic, anionic and non-ionic surfactants are normally added to help with the dispersion of our inorganic powders to create a nice slurry. We often add binders, things like PVB and PVA and PMMA are very common, and also plasticizers, things like polyethylene glycol. Now, if our tape or our support tapes are going to be based on electrode materials, then we require a lot of porosity in the final tape. And what we do there is we add a pore former. And these pore formers are small organic beads or fibres. These might be things like PMMA, polymethyl methacrylate, little beads that we disperse, and then when we heat those up, they burn out. This is sacrificial material that is removed in firing to create the required porosity. So if you recall, in our electrolyte supported tapes, we don't want porosity, we want them to be dense, so we want to avoid porosity. But in our electrode supported tapes, we actively have to add in additives like pore formers that can burn out the sacrificial material that gives us a high level of porosity in our final tape. So the slurry properties, we are very interested in the viscosity and the rheology, and what we really want to be working in, if we can help it, is a kind of Newtonian region whereby we've got linear shear stress, shear strain characteristics. So once you've made your slurry and you've put the tape down onto the polymer substrate, so your mylar, it then has to be dried in an oven. You have to control that drying rate to avoid defects. Typical defects that we can get include warping, cracks and delamination. We don't want defects in the green body, so that's the tape before it's sintered into the final ceramic piece, because if we've got defects in the green body, they'll be retained after sintering, and these defects will be detrimental to the final electrical properties. And the diagram here just shows you some typical common drying defects that we can get in tape cast layers. So you can get curling of the edges, or we can get crow footprint crackings, looks like birds' footprints here. And all these are due to the fact that we've not optimized the drying rate to remove some of the very highly volatile organics in the green films. When it comes to firing or sintering, then of course, as you know, sintering, the driving force is reduction in surface energy. So what we're trying to do here is to remove porosity. This is a diffusion controlled high temperature process. So the drying is mainly to remove the solvents, and the firing is to remove organics, say any pore formers that we've got if we're making an electrode support, and then finally to sinter to give us a mechanically robust body for our final piece. And again, to recap, the electrolyte support needs to be dense. If it's an electrode support, we require high porosity and a small grain size, because we want to have lots of triple phase boundaries present in our electrode supported bodies. So this just shows the apparatus that we have here in Sheffield to make button cells. So what we've got here is our tape casting unit that you see in the top diagram, and the cartoon of that apparatus on the right hand side that we've discussed previously. The lower diagram shows you our screen printer, which we can use to screen print on our electrodes. So in Sheffield, the way we make our button cells is it's an electrolyte supported cell. So here we're just showing you a tape cast layer of some 8YSZ onto a mylar background. So here's our polymer background, and here's our green tape, which you can see is flexible. It's 50% organics roughly and 50% YSZ. We then sinter them up at high temperatures to form our dense electrolyte membrane. We also shape these into circular discs because they're easier to use. So this is our 8YSZ, our dense electrolyte membrane. Typically density is somewhere between 95 and 98% dense. You need to be above the open porosity density, which for ceramics is approximately 92%. So if you're above 92% density, you won't have open porosity, and therefore your cells should be gas tight. And then we simply screen print on our cathodes and anodes, and that gives us our final button electrodes that we can use to test out either new materials, as new electrode materials, or to look at device performance under different microstructural changes to our slips involved in our electrode materials. So here I'm just showing some micrographs of some electrode supported solid oxide cells. You can see here, here's a typical electrode substrate after sintering. So the top diagram, you can see a high level of porosity. This dark regions here are the open porosity, and then what we do is we then deposit down a dense layer of what I said on top of that, where you can see now that there is very little porosity. So the previous slide showed you a cell that we were developing based on the electrolyte being the support layer. Here is another example where we've used the porous electrode substrate first, and then we've deposited down a dense layer of YSZ on top of that. So in summary, for the tape casting process to manufacture the substrate, you can see here that stage 1, we've got a precisely controlled manufacturing ceramic slurry which is placed in the initial chamber, and this chamber has a small gap which is controlled by the doctor blade. So the top part here shows us again this mixing of the ceramic powder and the solvents and the binders to homogenize this to form the slurry which goes into our tape casting unit, and with the doctor blade we can then control the thickness of this slurry onto the surface, and then this slurry goes past stage 2 onto stage 3, where it undergoes into a drying oven where we evaporate the liquid, forming a final solid tape on a polymer backing, and this tape then exits at stage 4 here, where it's wound onto a spool if you're doing a reel-to-reel process. So this is scalable, and it's a commonly used method in other ceramic technologies, in particular things like multi-layer ceramic capacitors based on barium titanate. These devices are mass produced using tape casting. So tape casting is a reel-to-reel scalable process for making thick films of ceramics. And by thick film we normally mean anywhere between a few microns up to say 100 microns. Now there is a web download that you can look at here that is an animation that's been produced by Morgan Technical Ceramics to show you the tape casting process, and I would recommend that you look at that online facility.